Hello everyone, I'm Yifan from UC Santa Cruz. Today I'm thrilled to share our work, PlanetServe, a decentralized, scalable, and privacy-preserving overlay for democratizing large language model serving. PlanetServe is directly inspired by PlanetLab, a landmark P2P network that allowed internet researchers to deploy and test their application across distributed nodes worldwide. We are applying that same overlay philosophy to LLM serving. The idea is that participants, including individuals, academic institutions, and small companies, volunteer their computing power and network resources. In return, they gain access to a shared infrastructure to deploying and testing their own LLM innovation at scale. But building a decentralized LLM serving system is not just a matter of connecting machines. We identify 4 fundamental research challenges. C1 is overlay organization. How do you structure decentralized nodes so they can collectively serve users reliably? C2 is anonymous communication. How do you prevent model nodes or other relay nodes from linking a prompt back to the person who sent it? C3 is overlay forwarding for efficiency. Without a centralized scheduler, how do you still achieve KV cache reuse and load balancing? C4 is decentralized model verification. How do you ensure that a model node is actually running the model it claims to run without relying on a trusted third party? To our knowledge, this is the first work to systematically study all these core challenges for scalable LLM serving over a decentralized overlay network. PlanetServe organized participants into 3 distinct roles. User nodes are clients. They want access to LLMs while keeping their identity private, and they can join and leave the network at any time. User nodes also act as relays in anonymous routing. Model nodes are GPU-backed servers, each running 1 or more complete LLM instances. They also participate in overlay forwarding, which I'll discuss shortly. Verification nodes form a small trust committee run by entities with established credentials, such as recognized universities' research team. Their job is to maintain the integrity of the system by running a Byzantine fault-tolerant consensus protocol and keeping consistent records of trustworthy model nodes and their reputation score. Now let's get into the core mechanism for the anonymous communication, the Secure Information Dispersal Algorithm, or SIDA. Here's how SIDA works. Step 1, the sender encrypts message M with a randomly generated AES key K, producing the ciphertext KM. Step 2 splits KM into N pieces using Robin's information dispersal algorithm, a K of N threshold scheme. Step 3 splits the key share in a key K into N shares using Shamir secret sharing, also a K of N threshold scheme. Although both are K of N threshold scheme, they serve for different purposes. Robin's IDA is an erasure coding technique optimized for efficient data dispersal. Any K fragment can reconstruct the ciphertext, but the fragments still contain encoded information about the data. So the secure guarantee is computational rather than perfect. In contrast, Shamir secret sharing provides information theoretical secrecy for the key itself. We therefore use IDA for efficiency ciphertext fragmentation and Shamir for strong protection of the encryption key. In normal case, the message is large while the AES key is typically small. This method preserves security and reduces network traffic. Step 4, build cloves. It packages each fragment MI with the corresponding key share KI into a unit called a clove CI. And step 5, multipath send. It sends each clove along a different path to the destination. The receiver only needs K out of N cloves to reconstruct both the key and the message, but with fewer than K cloves, an attacker learns nothing. Now let me show how SIDA fits into full anonymous routing protocol. Step 1 is preparation. The user contacts any verification nodes to download two signed lists, the user list containing the public keys and IP address of all active users, and the model node list, which records the IP address of each model node and the model it is running. These lists are signed by more than 2/3 of the verification committee, so the user can trust their integrity. We use onion routing only for the short proxy establishment phase, where the messages are tiny and failures are cheap, where the user selects the model node they want to query. Step 2 is proxy establishment. The user needs to set up n anonymous passes. In our case, n equals 4. For each pass, the user selects 3 random users from the user list and build an onion encrypt pass through them. In onion routing, the message is wrapped in multiple layers, like layers of an onion. For each relay node, it removes exactly 1 layer of the encryption to reveal only the identity of next hop. The last user of the pass becomes a proxy for the user. As a result, every relay only knows the node it received message from and the node it should forward message to. No single relay ever sees its entire path, so it cannot link the original sender to the final destination. Once the proxies are established, all subsequent communication only uses stored path IDs for forwarding. No more public key operations on the data path. Step 3, with proxy established, sending a prompt is straightforward. The user applies CEDA to the prompt, generating 4 cloves, and each clove is sent along one of the 4 established paths to its corresponding proxy. The proxy then forwards the clove directly to the target model node. The final hop is not anonymous, but by this point, the model node can't identify the original user. Step 4, reply. The model node applies CEDA to its response to, splits it into 4 cloves, and sends 1 clove to each of the user's proxy. The user reconstructs the response once it receives at least k equals 3 cloves. Importantly, there is no decryption or encryption in the data path, keeping the forwarding process lightweight. The content is credential unless an attacker simultaneously controls users on k or more of the n passes. Now let's talk about overlay forwarding, so specifically how to achieve KV cache reuse and load balancing across decentralized model nodes without a centralized scheduler. In cloud system, for example, a central router can maintain a registry of all cached prompt prefix across the cluster. When a new request arrives, the router can find the best prefix match and send the request there. We can do that. There is no central router in PlanetServe. The naive alternative is have every model node maintain a full copy of global registry, which has 2 fatal problems. First, high memory overhead. Second, high communication overhead. We solve both problems with a new data structure, hash registry or HR tree. The key insight is borrowed from Bloom filter or cuckoo filter. Instead of storing raw prefix tags, we store 8-bit hash fingerprints of variable length prompt chunks. This slashes memory by orders of magnitude. And because hashes are compact, delta update, broadcasting only what changes since the last snapshot are tiny. Our evaluation shows delta update reduced network recalls by roughly 10 times versus full broadcast. Each tree node also stores a pointer to a table entry, identifying which model node holds the corresponding KV cache, along with that node's load balancing factor and reputation score. So HR tree simultaneously captures the cache state, load balancing information, and trustworthiness, everything needed for intelligent forwarding decisions. When a model node receives a user's request, it executes the following logics. The first decision is whether the prompt prefix has an existing cache entry in the HR tree. If there's no cache hits, then the request follows the normal load balancing path. In this case, the system forwards the request with a node with best load balancing factor. If there's a cache hit, the system does not blindly forward the request to that node. It first checks whether the cache hit model node has a reputation score above the threshold, as cache reuse should not override reliability. If cache hit node is trustworthy, then the request is forwarded to that target model node. The load balancing factor depending on the moving average latency, queue length, and node capacity. The system also preserves session affinity by routing consecutive prompts in a conversation to the same model node while possible. Another challenge is trust. How do we know the model nodes are actually running the model nodes they claim? A dishonest node might run a smaller, cheaper model, or it might modify the prompts or return garbage outputs. Our approach is sampling-based verification. Verification nodes send challenge prompts through the same anonymous overlay, so the model nodes cannot distinguish probes from normal users. Each verification node runs its own local copy of the reference LLMs. When it receives a challenge response from a model node, as the sequence shown here, for example, William Shakespeare was a playwright. It will evaluate it token by token. For each token position, it computes the probability that its local reference model would assign to that specific token, given the token and the all preceding token. If they match, the node will get a higher credit score. Reputation is then updated over time. Under normal behavior, the system combines historical reputation with current credit. When the fraction of violation exists a threshold, the punishment will sharply reduce the reputation. Nodes whose reputation drops below a threshold are marked as untrusted and removed from routing. Now let's look at the evaluation, starting with the security. We compare PlanetServe with onion routing and garlic cast in a simulated 10,000 node network, verifying the fraction of malicious nodes. PlanetServe achieves slightly higher anonymity than both baselines and perfect confidentiality. Now let's look at the performance overhead introduced by anonymous routing. We measured 2 operations over 10,000 trials on 2-bench dataset. Both preparation and decryption are well under a millisecond at the tail. For context, LLM inference itself takes tens of seconds on the same dataset. The anonymity overhead is completely negligible compared to the inference time. This figure shows how reputation scores evolve over 35 epochs under 3 different punish sensitivity settings. We can see clear separation between the honest and dishonest behavior. Now for the end-to-end serving latency with and without HR tree, we run 4 workloads across 2 GPU configurations. Here we show the 8A100 GPUs serving DeepSeek R1 14B. We compare against a centralized baseline of the same hardware running standard VLM without KV cache sharing. Across all 4 workloads, tool use coding, LangDog QA, and the mixed workload. PlanetServe consistently reduced the average latency, P99 latency, and time to first token. The improvement is most pronounced on heavy workloads. For LangDog QA and mixed workload, where prompts are long and prefix sharing opportunities are high, the difference is dramatic. PlanetServe reduced time to first token by larger than 50% at higher request rate. So to wrap up, PlanetServe is a centralized overlay for LLM serving while preserving privacy, scalability, and trust. We designed an anonymous routing mechanism with minimal overhead. We proposed HR tree, which supports decentralized KV cache reuse and load balancing. In our experiments, this helps to reduce latency by more than 50%. We studied model verification. Our mechanism can detect dishonest node. Overall, PlanetServe demonstrates the decentralized LLM serving is a promising direction for making LLM access more open while keeping scalability and privacy preserving. Thank you, and I'm happy to take questions.